your program interacts with the outside world, well, the outside world has a state, and your inputs and outputs do things to that state that you must reason about. And what's the type of that state? Well, you get to choose. And so you choose, in essence, by instantiating this external specification, the specification of the outside world, the extension. And here, this program, I'm just choosing the trivial outside world whose state type is unit. Okay, but in the in the last talk tomorrow, which is about the DeepSpec web server and its specification in C and its verification in verifiable C, Leonard Beringer will give an example of reasoning about input-output in verifiable C. And for that, there will not be the trivial state of the outside world. All right. So we have to prove that all of the function bodies satisfy all their function specs. And this is our proof obligation. Here's a list of 2 function bodies. This is the program. This is what was parsed by the front end of CompCert. The SumArray function is an internal function with this function body, and the main function is a function with that function body. So that's a list of 2 things. Here's a list of function specs. There's one function spec for SumArray and another function spec for main. You should recognize this. This is what we claimed in our gprog. And now we just have to match up that there's a proof for each of these. So where's our proof that fSumArray relates to SumArray spec? That proof is body SumArray, which I proved up there. So if we apply the semexfunctcons tactic with body SumArray, it sort of picks off the first element of this and the first element of that and matches them up. And our remaining proof obligation is that this list matches up. Well, we have a proof that fmain satisfies main spec. That's called body main. And we prove that. We've proved the whole program. Okay. So back to here. The paradigm of applying, right, the very first part of this lecture was, what is the program logic? But now the next question is, how do you apply the program logic to the program? And you can do Hoare logic proofs in all sorts of ways. You can do backward Hoare logic proofs by starting at the end of your function and applying weakest precondition rules. You can do forward Hoare logic proofs. In separation logic, it's usually more convenient to do forward proofs, because then you don't get so many magic wand operators. And so we'll do forward symbolic execution using forward style separation Hoare rules with entailment solving as a subroutine. And that was demonstrated, in this 2005 paper by Burdine et al. They demonstrated it for very simple separation logic predicates that were just shape analysis. Shape analysis is just proving this is a linked list, who cares what its contents are, and this is an array, and so on. And you think of all the maps to operators, they have sort of underscores on their right-hand side for we don't care about what the contents are. But because we do care about the contents, and reasoning about the contents often involves reasoning in the mathematics of your application domain, we can't make it fully automatic here. So there's 2 ways to make it less than fully automatic. One that's taken by tools in the Boogie, Daphne, Verifast, Framacy, I think, style, which is use an external SMT solver and fill in lots of assertions in your programs to help guide it from one place to another. And that can work. But I like proving things in a proof assistant. Partly because I get to use higher order logics that way, partly because I don't have to figure out just the right lemma to trick the SMT solver into recognizing what I'm doing. So we'll do it interactively. All right. And I showed you the lifted predicates sort of in the theoretical sense, but The logic could have lifted predicates that are predicates P on an environment and a memory. But here we put them in a particular canonical form. We separate the pure propositional parts into one list, the local variable bindings into a second list, and the separation logic conjuncts into a third list. And this is mostly deeply embedded, right? The temp is a kind of syntactic inductive part of an inductive predicate for easy matching by the proof automation. But I say mostly deeply embedded because this part is a Coq value that is not deeply embedded. So dividing up the assertion into these parts is for the efficiency and convenience of the proof automation system, and maybe for the convenience of the user, maybe. And of course, sometimes we have an existentially quantified canonical form. You can put existential quantifiers deep inside, and that happens sometimes when you have user-defined predicates that have existentials. But then you generally want to hoist them to the outside by a kind of automatic rewriting so that you can intro them above the line. Now, you saw this kind of load before. If somewhere in the precondition we have y maps to wz, and we do the command x gets y dot head, then afterwards x should equal w. And there's the same load rule is used for field dereference, for array subscript, or even for the command x gets p dot foo sub 6 dot bar sub 7, right? There's some path of substructure, field selection, and array subscripting, as long as there's only one actual memory dereference in there. So the way we do that load rule is this derived lemma in separation logic. The simple version of load in the primitive proved sound separation logic doesn't look like this, but we can derive this as a lemma from that rule. And it looks complicated. Here's the precondition. The precondition for load matches any canonical form assertion. So you can just, the forward tactic is going to be applying this rule. So it's convenient for the forward tactic that it really will match anything. Then there's a bunch of premises, and all of these are just calculational. For example, the type of the expression being loaded from must not be a volatile type in the C programming languages. Right? It has to be ordinary memory. And this type is volatile equals false can be proved by just reflexivity, just simplification. It's proof by calculation. We look up the type of the variable being loaded into, and it has to be some type or other in delta, which is the global context. Well, delta is a trie data structure. It's a binary trie that you can calculate efficiently in log n time the lookup of a variable to get a type. So this proves quickly by reflexivity. We calculate the local variable bindings of the precondition into a couple of binary tries, one for the non-addressable local variables and one for the addressable local variables. And then we can do substitution on the expression with the values of those variables. So we get a fully substituted expression. Now, our operational semantics of C doesn't use substitution, but we can use it here because the proof of this whole lemma says, yes, that turns out to be equivalent. So we do the substitution, we get the evaluated expression E with the substitutions. And this is all efficient and proved by reflexivity quite quickly. All right. Then, sometimes there's a user-provided hint I don't think I showed you an example of that hint. But if so, it finds something above the line, and that's quick. And then the rest is all either calculational or pretty automatic. This is just proof by reflexivity on sort of the calculation about the field type of dereferencing a dot foo sub 3 from a particular C language root type. And then R is the SEP part of your prop local SEP, and there has to be the nth clause of R should be a field at, which is a generalization of data at that matches a certain thing. And your field path has to concatenate in a certain way, and your share has to be readable. This isn't proved usually by reflexivity or anything. This is just proved by auto from some proposition you have above the line about your share is readable, or from the hint database that says the extern writable share is readable, right? So every single one of these is easy to prove. We've rearranged the load rule of the original separation logic into one that's designed for easy application, because it matches any precondition, and then calculational and automatically provable subgoals. And that's sort of the secret to efficient forward symbolic execution. Yes, question?
So if you have a program that reads from a volatile memory, do you have a different rule for that, or is that something that's...
All right, if your program uses volatile variables in the C programming language, what do you do? Well, the ComCert front end, C LightGen, will transform that program into one where every access to a volatile variable is written as a function call to some external function whose job is to read or to write a volatile variable. And then you can reason about those using those functions, which can have sort of arbitrarily complex preconditions and postconditions that relate what happens before to what happens after. Okay, then look in the postcondition. Remember what forward does, right? You took a current assertion and it said, okay, here's your new assertion for afterwards. So that's the postcondition, and that's calculated here, right? This is load, so the SEP clause's memory isn't changed by a load. That's the same. No new facts of logic are true after a load than before. But your local variables have different values in them, maybe, because you assigned to ID. And so this is also just calculated from the original list of temp bindings to the new list. So everything's arranged for forward efficiency. And therefore, here's the forward tactic, right? Match the proof goal to, first reassociate your sequence of commands to find the first command that isn't actually a sequence, and then apply that lemma. Well, first apply the sequence rule, right? I have the command C1 followed by C2. So if I do apply of the sequence rule, then the postcondition will be a unification variable. The postcondition of C1, the precondition of C2. Since the postcondition is a unification variable, applying the lemma, with this conclusion can instantiate that unification variable. That's easy. Apply that lemma. The subgoals are almost all quite easy to discharge, just using ordinary calc tactics, such as reflexivity, and sometimes we write special tactics for certain patterns. Yes?
So you write apply, but you mostly use apply.
Yes, it's apply. Well, yeah. So that's the forward tactic. It just applies these special purpose constructed lemmas. Now let's talk about the entailer, right? The entailer is supposed to simplify entailments, solving the parts that it can and leaving a residue for the user. So the first thing it has to do is take your lifted entailment and produce a lowered entailment. So suppose your entailment is a lifted entailment. in the left-hand side, we have all these pure propositions. So you can move them directly above the line, right? It's assumed that in the pre-state, these mathematical facts are true. And these facts are independent of the pre-state, so we just move them above the line. Second, handle the local variables. And I think I'll skip this part because it's not always very interesting or useful. Now, for each of these local variables, underscore I1, underscore I2, and so on, we can just assume that the state, what's the state? We don't have a state now. We're going to have a state when we run the program. So we can treat that state abstractly, rho, and assume values for rho of I1 and rho of I2. And those will show up in S as well. So we just substitute them away. And now we're left with this entailment, which just has the sep part. So that's a lowered entailment. It's got some separating conjuncts on the left, and on the right it's got some pure Coq propositions and some separating conjuncts. So how do we solve lowered entailments? First, for each kind of separating conjunct, there's typically a pure propositional fact you can derive from it. For example, if I have data at that says at address A, there's a data structure with some contents, then I know that A is actually a pointer. It's not null pointer. It's not a floating point number. And so that's a pure propositional fact that I can just derive. And I know, for example, that the length of the contents equals the size of the declared type. So there's a hint database for each kind of separating conjunct that will derive some pure propositions and throw them above the line. Okay, then let's separate this right-hand side into two subgoals. This one, here we're doing something, as I showed you half an hour ago. Let's assume now that we can prove P1 prime and P2 prime just from what we have above the line, and that we no longer need these separating conjuncts, that we've extracted whatever pure propositions we want to from them. That's sometimes dangerous, but usually it's fine. And then we have this. This is the separating part of the proof obligation. So now we prove as many of the P prime as possible by auto or by other simple means, and leave the residue for the user to prove. And on this side, we can see if any of the R sub I match exactly the S sub I, and we can cancel them out. And finally, if we've canceled all of the S sub I except one that's left, that's basically a unification variable, we can cancel that way. And that's called frame inference. That's when I am calling a function, and some of my sep clauses match the precondition of the function, and others are left over, and the function doesn't need them. Question?
So how's the proving no alias contrary to the spirit of separation?
Well, here's a pure propositional fact that we can get from A maps to B separated from C maps to D, which is A is not equal to C. All right. Well, we could put that pure proposition above the line, A not equal to C, but it's not enough because not only A is not equal to C, but A plus 1 is not equal to C, and A plus, up to size of is not equal to C. And if we have n separating conjuncts, then there'll be n squared over 2 facts to put above the line. And the whole point of separation logic was to encode those quadratic number of anti-aliasing facts into a linear number of stars. So the way that you should reason about anti-aliasing is to reason in separation logic rather than in sort of inequalities in arithmetic. Now, this lemma exists in our system. You can apply it if you want to, but it's just not recommended. Okay, so the the summary of VST Floyd